Yep. Thank you very much for the introduction, and thank you to the organizer for this opportunity to give a talk here. So my topic today is non-local curvature with integrable kernel. So this is a joint project with my postdoctoral advisors in University of Nebraska-Lincoln, Professor Michael Voss and Professor Petronella Radu. So we started this project actually a year ago. So before we go to the non-local curvature, I just want to introduce about the classical one. So if we consider a C2 surface S and then any point P on that surface, and let's say E be the unit tangent vector in the tangent space, then because it's a C2 surface, then in the neighborhood of the point, we can write down that surface as a graph of C2 function, let's say phi. And then the directional curvature in the direction of E, we can define as this D2 phi of P, which is the Hessian acting on E, and then you take the inner product with E. So that gives me the directional curvature. So now, because this matrix is the real symmetric matrix, it has n-1 eigenvalues, and then let's say those eigenvalues are lambda 1 to lambda, basically the n-1, which are called principal curvature. Then we can define the mean curvature as basically the average of all those. So associated with this concept, there is also a theory called motion by mean curvature. And what is that? So in the mean curvature flow, basically you can think that for a bounded set, if we take any point on the surface or on the boundary of that set, then the motion along the perpendicular direction is basically proportional to the mean curvature. And that is or equal to the mean curvature. So that is the mean curvature flow. So maybe we can give an example which is sort of a discrete approximation of this mean curvature flow. So this example I took from Caffarelli's paper, which is actually given by Stanley Osher during the study of cellular automata. So this is a heat equation we can see, and so in this equation, we can let's say there is a set omega, and the initial data is basically the characteristic function. Then we define, so then we run this heat equation for epsilon time with this data, and then we define after epsilon time that we omega 1 to be the set where this U is greater than 1/2. And then again, we update the initial data U1 with the characteristic function of omega 1. So if we run that heat equation again and again, then there is a paper by Evans who shows that at each time, basically this boundary of this surface boundary of omega, which is the surface, actually converges to the minimal surface or motion by the mean curvature. So this is one discrete approximation. So there is another example where the where the mean curvature flow can be observed is the as the limit of phase field models involving the double well potential. So that is another example of that. And so another thing I want to introduce is the classical perimeter. So if the set with C2 boundary, in that case, the perimeter can be defined as the Hausdorff measure. Whereas in 1951, Cacciopoli, he gave a following definition of the perimeter. So for a set E, we can define the perimeter inside a set omega to be basically the supremum of this integration of the characteristic function and times this divergence of phi. But phi is a smooth function. So this is called basically the total variation of the characteristic function, chi e. So that's how we can we actually define the perimeter of any set. For a set with C2 boundary, this perimeter would basically coincide with the Hausdorff measure. So, this minimal surface problem is connected with this mean curvature problem. So now, if we go to the non-local curvature, in 2009, Caffarelli and Roque-Joffre, Savin, they considered the diffusion process with the fractional Laplacian. So they basically, if you go back to the diffusion process again here with the classical mean curvature flow, they replace that one by the fractional. And in that case, naturally, the energy functional is basically the HS norm of the U. And so they defined the non-local perimeter of a set to be the HS norm of the characteristic function. So then their result, and then they showed in that paper itself that the critical point of that energy functional is basically gives us a notion of the non-local curvature. And what is that guy? That is basically this integration of characteristic function of E minus characteristic function of the complement of E, and with this kernel of the fractional Laplacian. So that's how they define the non-local curvature with the fractional Laplacian kernel. Another important result in their paper was basically the regularity of the non-local minimal surface. And to get to that, I mean, what they define is they defined this functional, which is LAB, which is basically the which is basically the integration of characteristic function of A times characteristic function of B with this fractional Laplacian kernel. And with the help of this L, they define the local energy functional inside a set omega, which is basically this L of E intersection omega with EC, and L of E minus omega with the EC intersection omega. So once they define this local energy functional, then they try to minimize that. And that is their main result in their paper. They say that if E minimizes this local energy functional for the ball B1, then the hypersurface del E in the set B half is a C1 alpha hypersurface with the exception of a closed set. So that is the main result in their paper about this non-local minimal surface. But that is where actually the study of non-local mean curvature and non-local minimal surface appear. And I want to describe another problem with the same non-local mean curvature, which is the prescribed curvature problem. So there are two groups in 2018. Actually, they proved that for a C1 alpha hypersurface, if we want to study the constant non-local mean curvature problem, then the solution would be ball. And here the non-local mean curvature are the mean curvature which are defined by Caffarelli and Safin. So this group is one group is Chiralo, Figali, Maggi, and Novaga, and the other group is Cabre, Fall, Morales, and Boy. So they studied this non-local constant mean curvature problem. And in that, for their proof, the main ingredient is basically a non-local version of Alexander moving plane method. So we'll talk about that moving plane method for our case also. So this is the non-local mean curvature with the singular kernel basically. And so next we'll talk about the non-local mean curvature, mean curvature with the integrable kernel. And so this has been introduced by this has been introduced by Rossi and others, so the motivation behind studying this type of curvature is basically eliminate the restriction on the smoothness of the geometry of the domain. So I will let me give you an example of that basically. So if we think about an image which is a square like this, so I just drew the two sides of the square, which makes 45-degree angles with the x-axis, and then we want to measure basically the classical perimeter of the square with the help of let's say pixels. So these are my pixels basically. So what would happen that if you increase the resolution of the image, or that means if you are decreasing the length of the square pixels, I mean, no matter how much you increase the resolution, this pixel will always give you the classical perimeter, the computational classical perimeter as the actual perimeter times square root 2. So just to see that, so just think about this pixel. Let's say the size of the pixel is 2 delta. So then this pixel will contribute 8 delta in the computational part of the perimeter. Now, if you reduce that to half of the length, that means let's say that the size of this pixel is delta, then you will get 2 pixels instead of 1, but still those 2 pixels will contribute 8 delta to the computational perimeter. So we can see that I mean, no matter what the resolution is, no matter what the high resolution, it will always be the actual perimeter times square root 2. So with the help of non-local perimeter, we can basically reduce that error. Another thing is that with the integrable kernel, we can define non-local perimeter and non-local curvature also even at the corners. So that is another advantage. That is another advantage of computing the curvature in this way. So this is the motivation, and with that we define. I mean, the Rossi and others actually they define this idea of non-local perimeter using the same formulation as Caffarelli, but instead of singular kernel like the fractional kernel, they used an integrable kernel J. So this is how they define this non-local perimeter, and with that they also define this J-mean curvature at any point x to be the integration of the J times chi, the characteristic function at E minus the characteristic function at EC. So you can see that this definition is very similar to what Caffarelli and others introduced, but you just need to replace the fractional kernel by the integrable kernel. So, so now we are studying this. We are studying the constant mean curvature problem for this integrable in this integrable case for probably in the last 6 or 7 months. So we got some preliminary result in this case also. So what we did is we took a kernel J such that J is not highly singular, rather the bounds on J are basically C over absolute value of x to the power n minus alpha for some alpha greater than 0, and we also give some bound the growth condition on the gradient of the J. So in addition, we also assume that J is radially symmetric as in the fractional Laplacian case, strictly decreasing non-negative function, but now it is supported in a ball of radius r. So that is the difference between basically the fractional kernel and with this with our kernel. So in that case, if omega is a non-empty bounded, and we should say I forgot to add that if it is a connected state, open state with the C1 beta boundary, then we can prove that. And with the property that the non-local curvature is constant at every point, then we can prove that omega is a bond. So what is the idea behind the proof? Again, here in this case, the Alexandrov moving plane method is the key ingredient. And let me just briefly mention what do you mean by this moving plane method. So let's take E is a set with C1 boundary, and suppose this is a hyperplane, and for simplicity let us assume that hyperplane is x1 equals to lambda. So now E lambda, this set is basically the reflection of the set E with respect to this hyperplane. So there are another situation. I'll talk about that. So that's why I drew this situation also. So we'll talk about that. But so then what we are doing is we are moving this plane x1 equals to lambda to the left. So basically you can definitely see that once you move this the plane to the left, E and E lambda starts to intersect, right? So and then for some lambda, you will see that the the uh, the intersection of this E lambda with this negative side with the negative side of this hyperplane will still be inside the set E, but there would be one lambda which is the critical lambda. After that, the negative side of this E lambda will be outside the set. So and for that critical lambda, two things can happen. One is like you can this E lambda will intersect or touch at an interior point at the boundary of E, or it can happen that at the intersection point, let's say here, the tangent the E vector would be a tangent vector at that point on the surface. So the first one is the first case is called interior touching. The second one is called the non-transversal intersection. So for any set E with the C1 boundary, if you do this moving plane, then either of those two incident happen. Okay, so now with that idea, what we do is we need to compare the curvature at the point of intersection or at the point of touching of E and E lambda. So that's what we did, and that would lead us to the conclusion that E and E lambda are same set. And what is the meaning of that? So when you say E and E lambda are same set with respect to this hyperplane, that means with respect to that hyperplane, E and E lambda, E is symmetric. Now, this is true for any hyperplane, and that gives us that E is actually a point. So that's the idea of the proof, right? Which I already described here. So in this proof technique, we use the strictly decreasing property of the kernel, as in the singular case, but we need to modify our proof due to the finite support set of J, basically, because J has a jump. J can have jump at some point in the I mean after the ball BR, basically after the support set BR. So we need to modify the proof for that also. So we are currently considering the following cases. If the kernel is not strictly decreasing, let's say J equals to 1. So that case is also, we are kind of got the similar result, but we are still working just to check. And the other one is basically to get this solution in the set of surfaces which has continuous boundary. And that is a difficult problem in a sense that we cannot use the Alexandrov moving plane method in this case. So we are still working for this scenario. So with that, I want to thank you all, and